Hi, good day, everyone. I am Kwang from Henderson, Nevada, USA. Today, I will present my research results on generalized Fibonacci sequences. So let's start from the beginning. The famous Fibonacci numbers f of n is a sequence of integers start with 0 and 1. Then the subsequent numbers are equal to the sum of two previous numbers. The Lucas numbers L of n is a companion sequence of Fibonacci numbers. It starts with 2 and 1. Then the subsequent numbers are equal to the sum of two previous numbers. In other words, they satisfy the recurrence relation A of n equals A of n minus 1 plus A of n minus 2 for n greater equals 2. Then x squared minus x minus 1 equals 0 is the characteristic equation. Let u and v be the roots of this equation. We can have binary formulas for Fibonacci numbers and Lucas numbers. For Fibonacci numbers, f of n equals u to nth power minus v to nth power divided by u minus v. For Lucas numbers, L of n equals u to the nth power plus v to the nth power. Both f of n and L of n have very elegant sum formulas. F of n is equal to j plus 1 factorial divided by I factorial times j factorial, where I and j are the indices satisfy I plus 2 times j equals n minus 1. L of n is equal to the sum of n times I plus j minus 1 factorial divided by the product of I factorial and j factorial, where I and j are the indices satisfy I plus 2 times j equals n. Next, I will talk about the Gerard-Warren formula and its relation to Lucas numbers. F of x is a moniker polynomials of degree k with coefficients a0, a1 up to ak, with a0 equals 1. We assume that f of x has distinct roots x1 up to sk. Then the Gerard-Warren formula is the following. the sum of nth powers of the roots is equal to a sum of the products of powers of the roots, multiplied with n times factorial of sums of powers minus 1, divided by product of factorials of the powers. In the formula, the indices J1 up to Jk, which are the powers of the roots, satisfying J1 plus 2 times J2 plus up to k times Jk is equal to n. The Banach formula for Ln is equal to u to the nth power plus v to the nth power. So we may consider the sums of nth powers of the roots are a generalization of Lucas numbers. In the next slide, I put the information in previous slides in a table so we can compare the information side by side. In the first column, we have Banach's formula and some formulas for Fibonacci numbers. In the second column, we have Banach's formula and some formula for Lucas numbers, and a definition and a sum formula for the generalized Lucas numbers. The question mark in the first column indicate that we shall have a generalized Fibonacci numbers, which is similar to the generalized Lucas numbers, and a sum formula for generalized Fibonacci numbers, which is similar to the Gerard-Warren formula. And this is the motivation of this research. Find a nice generalization of Fibonacci numbers, which has a nice sum formula. There are many generalizations of Fibonacci numbers. There are just two numerals to be discussed in this short presentation. My generalization has many other generalizations as special cases. In the next slide, I will show the form of my generalization of Fibonacci numbers and the form of some formulas. We will define a generalization of Fibonacci numbers as a sum of the powers of the roots divided by something. We will have a sum formula which is equal to a sum of products of powers of coefficients with a quotient of factorials. In the next slide, I will give more details on what new sum formula looks like. The sum formula is equal to a summation of powers of the roots times the sum of powers factorial divided by the product of factorials of the powers. And where the indices J1, J2 up to Jk satisfy J1 plus 2 J2 up to k times Jk equals n plus a number, which we will determine later. In the next slide, I will show a generalization of Fibonacci numbers, which involves the derivative f tick x of f of x. P of n is equal to a sum of nth powers of the roots xi divided by the value of first derivative at xi, the value of derivative at xi. And if f of x equal to x squared minus x minus 1, then P of n is the Fibonacci numbers. If f of x equals to x cubed minus x squared minus x minus 1, then P of n is the Fibonacci numbers. In this formula, I give a detailed sum formula for the generalized Fibonacci numbers. In this formula, the sum of I times ji is equal to n minus k plus 1. And the next two bullets are the formulas for quadratic and cubic polynomials. Next, I want to talk about generative functions for generalized Fibonacci numbers and generalized Lucas numbers. The generative functions for P is equal to the reciprocal of x divided by f at the reciprocal of x. The generative functions for Q, the generalized Lucas numbers, is equal to a reciprocal of x times f tick of reciprocal of x divided by f at the reciprocal of x. Using the formulas of generating functions, we can prove the following identity. Q of n equal to f tick P of n. This shows the relation between generalized Lucas numbers and generalized Fibonacci numbers. So we may consider generalized Lucas numbers as companion sequence of generalized Fibonacci numbers. We can also use the generating functions to prove the sum formulas for the generalized Fibonacci numbers. A Horrendous sequence has initial values a and b, and the entry satisfy recursion relation Wn equals p times w of n minus 1 minus q. of n minus 2. Our definition of generalized Fibonacci numbers and generalized Lucas numbers do not include Harridan sequence, but any Harridan sequence is a linear sum of generalized Fibonacci numbers and generalized Lucas numbers. So we can apply our formula to Harridan sequences. So use our formulas or some formulas, then we can prove of some formulas for Harridan sequence, as shown in this slide. And T of n is a function which equals 0 if n is odd, and T of n equals minus q to the 1/2 of n's power if n is even. Okay, please note that in this formula, the index I starts from 1, and index j starts from 0. There are 2 more slides of examples which shows the generating functions and identities of generalized Fibonacci numbers in terms of the generalized Lucas numbers in terms of generalized Fibonacci numbers. This is second slide. Yeah, this is the end of my presentation. I post all my research works on ResearchGate since my paper is published in 1972. Okay, I welcome any suggestions or any comments on my research works. Thank you.